Hello and welcome to the Quiet Cosmos. If you enjoy slow, thoughtful journeys through the universe, feel free to like the video and subscribe for more. And before we begin, let me know where you're watching or listening from tonight. Whether you're under a clear sky filled with stars or somewhere the clouds are hiding them away, it's nice to imagine all of us in different places sharing the same universe and perhaps wondering the same quiet question. Because tonight we're going to explore something that sits right at the edge of human understanding. What came before the Big Bang? It's a simple question, almost childlike in the way it's asked, and yet it leads us towards some of the deepest ideas in modern science, and some of the most surprising possibilities about reality itself. For a long time, the Big Bang has been described as the beginning of everything, the moment when the universe sprang into existence, expanding, cooling, and slowly becoming the vast cosmos we see today. But when we look more closely, that description begins to soften, because the Big Bang theory doesn't actually describe the beginning of everything. It describes the early evolution of the universe from an incredibly hot, dense state, outward. And when we try to look earlier than that, into the very first fraction of a second, our best theories begin to blur. Time itself becomes uncertain, space behaves in unfamiliar ways, and the laws of physics, so reliable everywhere else, start to fall silent. So we're left with a question that may not have a simple answer. Was there something before the Big Bang, a previous universe, slowly collapsing before expanding again, a quantum fluctuation, emerging from a strange, restless vacuum, a deeper structure of reality, where time doesn't even exist in the way we experience it? Or perhaps the question itself needs to change. Because if time began with the Big Bang and then asking what came before it, may be like asking what lies north of the North Pole. And yet scientists continue to explore this boundary. They build theories, they test ideas, they look for faint signals, subtle patterns in the oldest light in the universe that might hint at something earlier, something deeper. Not because we expect an easy answer, but because the act of asking the question reveals something important about the universe and about us. So tonight, we'll take our time, we'll move slowly through what we know, what we don't know, and what might lie just beyond the edge of both. And as we do, you might find that the question changes shape, becoming less about a single moment in time, and more about the nature of time itself. So wherever you are, however you're listening, just settle in. And let's begin, gently, at the beginning. What came before the Big Bang? It is a question that feels almost impossible not to ask. The moment we hear that the universe had a beginning, something in us leans gently backward, as if trying to look just beyond it. We imagine a timeline stretching into the past, and we expect that if we follow it far enough, we will find something waiting there. Another moment, another state, another story, because that is how our experience of time works. Every day, every memory, every cause and effect we have ever known follows a simple pattern. There is always something before. Before this moment, there was the one just behind it. Before that, another and another, stretching back through hours, years, and centuries. Even when we reach the edges of recorded history, we still assume that something must have been happening just out of view. So when we hear that the universe began around 13.8 billion years ago, our instincts respond in a very familiar way. What happened before that? It feels like a reasonable question, almost unavoidable. And yet, as we begin to explore it more carefully, something subtle begins to shift. Because the Big Bang is not quite what it first appears to be. It is often described as a beginning, but in scientific terms it is better understood as a description of how the universe behaved in its earliest observable state. It tells us that the universe was once extremely hot, extremely dense, and that space itself has been expanding ever since. This understanding is built on careful observations. The work of Edwin Hubble in the 1920s revealed that distant galaxies are moving away from us, with their light stretched toward the red end of the spectrum. This redshift suggests that space itself is expanding. Later, in the 1960s, Arno Penzias and Robert Wilson discovered the cosmic microwave background, a faint glow of radiation that fills the universe and carries the imprint of its early hot state. Together, these observations form a remarkably consistent picture, but they do not tell us everything. They describe the evolution of the universe after a certain point. They allow us to trace the cosmic story back to a time when the universe was about 1 second old then to a fraction of a second, and even further to a moment known as the Planck time, which is roughly 1 divided by 10 raised to the power of 43 seconds. And beyond that point, our theories begin to falter. So when we ask what came before the Big Bang, we are not just asking about an earlier event. We are stepping into a region where the familiar rules of time and space may no longer apply. This is where the question becomes both scientific and philosophical. On the scientific side, we are asking whether there is a physical description of the universe that extends beyond its earliest known state. Could there have been a previous phase, a different configuration of matter, energy, or even something more fundamental? On the philosophical side, we are asking whether the idea of before even makes sense in this context. If time itself is part of the universe, and if it has a beginning, then what does it mean to ask about something earlier? It is a little like standing at the North Pole and asking which direction leads further north. The question feels natural, but the structure of reality may not support it. Physicists have approached this puzzle in different ways. Stephen Hawking, working with James Hartle, proposed what is known as the no-boundary proposal. In this model, the universe does not have a sharp beginning in time. Instead, time behaves more like a spatial dimension near the origin, smoothing out the boundary in a way that removes the need for a before. In Hawking's own words, asking what came before the Big Bang might be similar to asking what is south of the South Pole. Roger Penrose, on the other hand, has explored a very different possibility. In his theory of conformal cyclic cosmology, the universe does not have a single beginning, but instead goes through an endless sequence of cycles. Each cycle begins with a Big Bang and expands over vast stretches of time, eventually becoming so dilute that the distinction between very large and very small scales begins to fade. In that state, the universe can be reinterpreted as the beginning of a new cycle. In this view, what came before the Big Bang is not nothing, but a previous universe. These two perspectives highlight something important. Even among leading physicists, there is no single agreed answer to this question. Instead, there are multiple ways of thinking about it, each grounded in different assumptions about the nature of time, space, and the laws that govern them. And this diversity of ideas is not a weakness. It is a sign that we are exploring the edge of what is currently understood. As we move forward, it helps to hold on to a simple idea. The question itself may change. At first, it sounds like we're asking for a missing piece of a timeline, as though the universe were a story with a hidden first chapter. But as we look more closely, we may find that the structure of the story is not what we expected. Time may not stretch endlessly into the past. It may emerge from deeper processes or behave differently under extreme conditions. The very concept of before may depend on the framework we're using. So rather than rushing toward an answer, we can allow the question to unfold slowly. What came before the Big Bang? It might lead us to earlier universes, or to quantum fluctuations, or to entirely new ways of thinking about reality. It might even lead us to the realization that some questions are shaped by assumptions that do not always hold, and that is part of what makes this exploration so quietly fascinating. Because at its heart, this is not just a question about the universe, it is a question about how we understand beginnings, endings, and the flow of time itself. And as we continue, we will see that each possible answer does not simply fill in a gap. It reshapes the question in a slightly different way, gently guiding us, step by step, toward a deeper sense of what it means to ask where everything came from. When people first hear the phrase Big Bang, it often brings to mind something dramatic, a sudden explosion, a burst of energy erupting outward into empty space. It is an understandable image. After all, the words themselves seem to suggest it. But in scientific terms, that picture is not quite right. The Big Bang was not an explosion in space, it was an expansion of space. This distinction may sound subtle at first, but it changes everything about how we understand the early universe. In an ordinary explosion, there is a center, a point where everything begins, and matter moves outward into the space around it. Debris flies in all directions, spreading into a pre-existing environment. But the Big Bang does not work like that. There is no center. There is no outer edge that matter expands into, and there is no pre-existing space waiting to be filled. Instead, space itself stretches. Every region of the universe moves away from every other region, not because it is flying through space, but because the space between them is expanding. If you could imagine drawing a grid across the universe, you would not see objects moving across the grid. you would see the grid itself expanding, carrying everything along with it. A helpful comparison is the surface of a balloon. If you place small dots on the surface and then slowly inflate the balloon, each dot moves away from every other dot. There is no special point on the surface that acts as the center of the expansion. From the perspective of any single dot, it appears as though everything else is moving away. Of course, the balloon analogy has its limits. The surface is two-dimensional, while our universe has 3 dimensions of space, and the balloon expands into an external environment. The universe does not expand into anything that we can observe. Still, the analogy captures the key idea. The Big Bang describes the expansion of space itself. This understanding began to take shape in the early 20th century, when astronomers started to observe something unexpected about distant galaxies. In the 1920s, Edwin Hubble carefully measured the light coming from galaxies beyond our own Milky Way. By studying the spectral lines of this light, he noticed that many of them were shifted toward the red end of the spectrum. This effect is known as redshift. When light stretches to longer wavelengths, it becomes redder, and in this case, the stretching was not caused by the motion of galaxies through space alone, but by the expansion of space itself. The farther away a galaxy was, the more its light had been stretched. Hubble found a remarkably simple relationship. The distance to a galaxy is proportional to its recessional velocity. In other words, the farther away something is, the faster it appears to be moving away from us. This relationship is often expressed as velocity equals the Hubble, constant multiplied by distance. It is one of the most important observations in cosmology, and it suggests something profound. If everything is moving away from everything else today, then in the past everything must have been closer together. Follow that idea far enough backward, and the universe becomes smaller, denser, and hotter. Eventually we reach a state where the density and temperature are so extreme that matter as we know it cannot exist in its usual forms. This is the early universe described by the Big Bang model. Further evidence came several decades later in the mid-1960s, when Arno Penzias and Robert Wilson were working with a radio antenna at Bell Laboratories. They were attempting to measure faint signals from space, but kept encountering a persistent background noise. No matter where they pointed the antenna, the noise remained. At first, they considered a wide range of possibilities, including technical issues and even the presence of nesting pigeons in the equipment. It turned out not to be pigeons, which was probably a relief for both the scientists and the pigeons. What they had discovered was the cosmic microwave background. This radiation is a faint glow that fills the entire universe. It is remarkably uniform with a temperature of about 2.7 degrees above absolute zero. It represents the cooled remnants of the intense heat that filled the universe when it was only a few 100,000 years old. At that time, the universe was hot enough that electrons and protons could not combine to form neutral atoms. Light was constantly scattered, unable to travel freely. As the universe expanded and cooled, it eventually reached a point where atoms could form. This process is known as recombination. Once neutral atoms formed, light could move freely through space. The cosmic microwave background is that light, stretched over billions of years by the expansion of space. It is, in a sense, a snapshot of the universe when it was very young. Modern missions, including the Wilkinson Microwave Anisotropy Probe and the Planck satellite, operated by NASA and the European Space Agency, have mapped this radiation in extraordinary detail. These measurements reveal tiny variations in temperature, which correspond to slight differences in density in the early universe. Over time, those small variations grew into the large-scale structures we see today, including galaxies, clusters, and vast cosmic filaments. So the Big Bang model is supported by multiple lines of evidence: the expansion of the universe, the cosmic microwave background, the abundance of light elements such as hydrogen and helium, which were formed during the early moments of cosmic history. Together, they form a coherent and well-tested framework. But it is important to understand what this framework actually describes. The Big Bang model tells us how the universe evolved from a very hot, dense state. It allows us to trace the history of the cosmos back through time, from the formation of galaxies to the first atoms, and even further, to the first fractions of a second after expansion began. We can describe events such as nucleosynthesis, when light elements formed within the first few minutes. We can explore the decoupling of matter and radiation, which occurred after a few 100,000 years. We can follow the gradual formation of stars and galaxies over billions of years, and yet there is a boundary. As we move closer to the earliest moments, the conditions become more extreme, and our theories become less certain. At around 1 divided by 10 raised to the power of 43 seconds, a time known as the Planck time, the known laws of physics can no longer be applied with confidence. General relativity, which describes gravity and the large-scale structure of space-time, and quantum mechanics, which governs the behavior of particles at the smallest scales, both become essential. But they do not yet form a single unified theory. So the Big Bang model does not describe the absolute beginning of everything. It describes the earliest phase of the universe that we can currently understand. This is an important distinction. When we say that the universe began with the Big Bang, we're often using a simplified description. In practice, what we mean is that our current theories allow us to describe the universe back to a certain point, beyond which those theories no longer provide clear answers, and that leaves room for deeper questions. If the Big Bang describes the expansion and evolution of the universe, then what set those conditions in the first place? Why was the universe so hot and dense? Why did it begin expanding? Was there a prior state, or a different phase that led to this one? Or is the concept of a prior state something that only makes sense within the framework of time as we experience it? These questions take us beyond the standard Big Bang model and into the realm of theoretical cosmology. It is here that ideas begin to branch out. Some suggest that the universe emerged from quantum fluctuations. Others propose that there was a previous universe that contracted before expanding again. Still others explore the possibility that time itself may have a beginning, making the idea of before fundamentally undefined. But before we follow those ideas further, it helps to pause for a moment and appreciate what we have already uncovered. The universe is expanding. It was once hotter and denser, and the traces of that early state are still visible, quietly filling the cosmos with a faint glow of ancient light. The Big Bang, then, is not a single moment of creation in the way we might first imagine. It is a description of change, a story of expansion, cooling, and transformation. And like any story, it begins at a certain point, not because nothing existed before, but because that is where our understanding currently starts. Beyond that point, the picture becomes less clear, and it is precisely in that uncertainty that the question begins to open up again, inviting us to look just a little further into the quiet space where our knowledge fades and new ideas begin to take shape. As we continue tracing the universe backward, following the steady logic of expansion, something interesting begins to happen. At first, everything behaves in ways that feel familiar, at least to physicists. Galaxies move apart, radiation cools, matter forms. The equations of general relativity and quantum mechanics describe these processes with remarkable precision. But as we move closer to the earliest moments, the conditions become more extreme. Temperatures rise, densities increase, energies climb to levels far beyond anything we can reproduce on Earth, even in the most powerful particle accelerators built at places like CERN. And eventually we reach a point where our understanding begins to fade. This point is known as the Planck epoch. It occurs at a time roughly equal to 1 divided by 10 raised to the power of 43 seconds after the beginning of expansion. That is an unimaginably brief moment. To give some perspective, if 1 second were stretched to the age of the universe, this interval would still be far smaller than a single blink. During the Planck epoch, the universe was compressed into an incredibly small volume, with temperatures around 10 raised to the power of 32 degrees Kelvin. At these scales, the distinction between space and time begins to blur, and the familiar structure of space-time may not even exist in the way we understand it. And most importantly, our two most successful theories of physics begin to conflict. On one side, there is general relativity, developed by Albert Einstein in 1915. This theory describes gravity not as a force in the traditional sense, but as the curvature of space-time itself. Massive objects bend space-time, and this curvature guides the motion of matter and light. General relativity works exceptionally well on large scales. It accurately predicts the motion of planets, the behavior of stars, the dynamics of galaxies, and even the expansion of the universe. On the other side, there is quantum mechanics, developed in the early 20th century by physicists such as Niels Bohr, Werner Heisenberg, and Erwin Schrödinger. This framework describes the behavior of particles at the smallest scales, where uncertainty, probability, and discrete energy levels dominate. Quantum mechanics is equally successful, but in a very different domain. It governs atoms, electrons, photons, and the interactions that take place within them. It has been tested with extraordinary precision, forming the foundation of modern technology, from semiconductors to lasers. Individually, these two theories are incredibly powerful, but when we try to apply them together, especially under extreme conditions like those in the early universe, they do not fit neatly. General relativity treats space-time as smooth and continuous, like a gently curved fabric. Quantum mechanics, however, suggests that at very small scales, reality is discrete, uncertain, and subject to fluctuations. When we attempt to describe a situation where both strong gravity and quantum effects are important, such as near the beginning of the universe, the equations begin to produce infinities. These infinities are not just large numbers, they are signs that the theory itself is no longer working as intended. This brings us to the concept of a singularity. In the context of cosmology, a singularity is often described as a point of infinite density and temperature, where the known laws of physics break down. It is sometimes portrayed as the exact beginning of the universe, but it is important to understand that a singularity is not necessarily a physical object. It is better understood as a signal. A singularity indicates that our current mathematical description has reached its limit. It is the point where the equations no longer provide meaningful answers. So when we say that the Big Bang begins with a singularity, we are really saying that our current theories cannot describe what happens at that point. It is not a place we can directly observe, and it may not exist in the way the equations suggest. Instead, it marks the boundary of our understanding, and beyond that boundary, new ideas are needed. This is where the search for a theory of quantum gravity begins. Quantum gravity aims to unify general relativity and quantum mechanics into a single framework that can describe both the large-scale structure of the universe and the smallest quantum processes. Several approaches have been developed over the past few decades. One of the most prominent is loop quantum gravity, associated with physicists such as Carlo Rovelli and Abhay Ashtekar. In this framework, spacetime itself is not continuous, but composed of tiny, discrete units. These units form a kind of network, sometimes described as a spin network, where space is quantized at the smallest scales. In loop quantum gravity, the classical singularity may be replaced by a different structure. Instead of collapsing into an infinite point, the universe could reach a minimum size and then expand again, a scenario sometimes referred to as a bounce. Another major approach is string theory, which proposes that the fundamental building blocks of the universe are not point-like particles, but tiny vibrating strings. These strings can oscillate in different ways, giving rise to the various particles and forces we observe. String theory naturally incorporates gravity and suggests the existence of additional dimensions beyond the familiar 3 dimensions of space, and one of time. These extra dimensions are typically thought to be compactified, or curled up at extremely small scales. Within this framework, the early universe might be described in terms of higher dimensional dynamics, where the concept of a singular beginning is replaced by more complex interactions. Alongside these well-known approaches, there are also alternative ideas that offer different perspectives on the structure of spacetime. One example is causal set theory, developed by Raphael Sorkin and others. In this model, spacetime is not a smooth continuum, but a discrete set of events connected by causal relationships. Each element in the set represents an event, and the structure of spacetime emerges from the ordering of these events according to cause and effect. In this view, the fabric of the universe is more like a growing network than a continuous surface. The concept of time is tied directly to the sequence of events, rather than being a separate dimension that exists independently. Causal set theory suggests that, at the deepest level, reality may be fundamentally discrete and relational. Each of these approaches attempts to move beyond the limitations of current theories. They aim to provide a more complete description of the universe under extreme conditions, including those present near the beginning. But so far none of them has been fully confirmed. There is no single theory of quantum gravity that has been experimentally verified in the way that general relativity or quantum mechanics has. This means that when we ask what happened before the Big Bang, we're entering a region where our answers are still tentative. We can explore possibilities, we can build models, we can test certain predictions, but we do not yet have a definitive description. And that is an important point to hold on to, because it reminds us that the question itself may reach beyond the current boundaries of physics. When we ask what came before the Big Bang, we're not just asking about an earlier moment in time. We're asking about a regime where the very concepts of time, space, and causality may behave differently, or may not apply at all in the way we expect. It is a little like trying to describe the behavior of water before we understand molecules. We can observe patterns, we can make predictions. But without a deeper framework, there are limits to what we can say. So the breakdown of physics at the Planck epoch is not a failure. It is an invitation. It marks the edge of what is currently known and points toward the need for new ideas, new theories, and new ways of thinking about reality. And somewhere beyond that edge, if such a place can even be meaningfully described, may lie the answer to the question that started all of this. Or perhaps something even more surprising. A realization that the question itself is shaped by assumptions that do not quite hold at the deepest levels of the universe. There is a quiet assumption hidden inside the question we have been exploring. It is so familiar that it often goes unnoticed. When we ask what came before the Big Bang, we're assuming that time stretches backward in the same way it stretches forward. We imagine a timeline, like a long thread, extending endlessly into the past, and we place the Big Bang somewhere along that thread, perhaps near the beginning, but still surrounded by moments that came before it. But what if that assumption is not correct? What if time itself has a beginning? This idea can feel slightly unsettling at first. After all, time is the framework we use to understand change, sequence, and causality. It is the backdrop against which everything happens. Removing it, even conceptually, can feel like removing the stage from beneath a play. And yet, modern physics suggests that time may not be as fundamental as it seems. In the context of general relativity, time is not a separate universal flow that ticks the same everywhere. Instead, it is part of space-time, a unified structure that combines 3 dimensions of space with 1 dimension of time. The geometry of space-time can bend, stretch, and curve under the influence of mass and energy. This means that time can behave differently depending on the conditions. Near a massive object, such as a neutron star or a black hole, time passes more slowly relative to regions farther away. This effect, known as gravitational time dilation, has been measured experimentally using precise atomic clocks. So even within our current understanding, time is not absolute. But as we move toward the earliest moments of the universe, something even more unusual may happen. Time itself may lose its meaning. One of the most well-known attempts to describe this idea comes from Stephen Hawking and James Hartle, who proposed what is called the no-boundary proposal. In this model, the universe does not begin with a sharp edge in time. Instead, as we approach the earliest moments, the distinction between time and space begins to fade. To understand this, it helps to imagine a simple geometric surface, like the surface of a sphere. A sphere has no edges. You can travel across its surface in any direction, and you will never encounter a boundary. Yet, it is still finite in extent. Hawking and Hartle suggested that something similar might apply to the universe. Near what we think of as the beginning, time behaves more like a spatial dimension. The geometry of space-time becomes smooth and rounded, rather than having a sharp starting point. In this framework, there is no moment that can be identified as the absolute beginning of time. Instead, time emerges gradually from a region where the usual distinction between time and space does not apply. Hawking famously compared this to asking what lies south of the South Pole. It is a question that seems meaningful at first, but once we understand the geometry of the Earth, we realize that the concept of south simply does not extend beyond that point. In the same way, if time begins with the Big Bang, then asking what came before it may be a question that does not have a well-defined answer. But this is not the only way to think about time. Some physicists have gone even further, suggesting that time may not exist as a fundamental aspect of reality at all. Julian Barber, for example, has proposed a radical idea often referred to as a timeless universe. In his view, the universe does not evolve through time in the way we usually imagine. Instead, it consists of a vast collection of possible configurations which he calls Platonia. Each configuration represents a complete arrangement of the universe at a given instant. What we perceive as the flow of time is, in this picture, a sequence of these configurations connected by relationships that give the impression of change. But fundamentally, there is no external time parameter driving this sequence. There is only the structure of the configurations themselves, This idea can feel abstract, but it addresses a deep issue in physics. When we attempt to combine general relativity and quantum mechanics, time often disappears from the fundamental equations. The Wheeler-DeWitt equation, for instance, which attempts to describe the quantum state of the entire universe, does not contain a time variable in the usual sense. This suggests that time, rather than being a basic ingredient of reality, may emerge from deeper processes. Carlo Rovelli offers another perspective through what is known as relational quantum mechanics. In this framework, time is not something that exists independently of physical systems. Instead, it arises from the relationships between those systems. According to Rovelli, the properties of objects are not absolute. They only exist relative to other objects. The same applies to time. Time is not a universal background that flows uniformly everywhere. It is a measure of change defined by the interactions between systems. Clocks do not measure time because time exists independently. They measure change, and we interpret that change as time. This idea aligns with a broader trend in modern physics, where fundamental concepts are increasingly understood in terms of relationships rather than absolute quantities. If time is relational, then its meaning depends on the existence of interactions, and near the beginning of the universe, where the structure of space-time itself may not yet be fully defined, those interactions may not exist in the usual way. This leads to another intriguing possibility. What if space-time itself is not fundamental? Fotini Markopoulou has explored the idea that space and time may emerge from a deeper pre-geometric structure. In this view, the familiar concepts of distance and duration arise from more basic elements, somewhat like temperature emerges from the collective motion of particles. At very small scales, the universe may be described by networks of relationships or quantum information without any notion of space or time as we understand them. Only when these elements organize in certain ways do space-time and its properties appear. If this is the case, then asking what happened before the Big Bang may be similar to asking what temperature existed before particles began moving. The question assumes a framework that may not yet be applicable. Taken together, these ideas suggest a profound shift in perspective. Time, which feels so immediate and fundamental in our daily experience, may be a derived concept. It may emerge from deeper physical processes, and it may not extend indefinitely into the past. So when we ask what came before the Big Bang, we may be reaching beyond the domain where time has meaning. This does not mean that nothing existed. It means that the language we are using, the idea of before and after, may not apply in the way we expect. The universe, at its most fundamental level, may not be a story unfolding in time. It may be something more subtle, a structure, a set of relationships, a configuration that gives rise to the experience of time rather than existing within it. And if that is the case, then the question we started with begins to transform. Instead of asking what came before the Big Bang, we might ask how time itself emerges, or what underlying processes give rise to the appearance of a beginning. It is a gentle shift, but an important one, because it moves us away from the idea of searching for a hidden moment in the past and toward the deeper question of how the very notion of a moment comes into being, and in that space where time itself becomes uncertain, the universe begins to feel a little less like a timeline, and a little more like something still waiting to be fully understood. As we move closer to the earliest moments that physics can meaningfully describe, the universe begins to reveal something both elegant and unexpected. It appears, for a brief and extraordinary period, to have expanded at a rate far beyond anything we see today. This idea is known as cosmic inflation. It was first proposed in the early 1980s by Alan Guth, and later developed further by Andre Linde and others. Inflation was not originally introduced to explain what came before the Big Bang, but rather to solve a set of puzzles within the standard Big Bang model itself. And yet, as often happens in science, the solution to one question opened the door to many others. To understand why inflation is needed, it helps to consider what the universe looks like on the larger scales. When we observe the cosmic microwave background, that faint radiation left over from the early universe, we find that it is remarkably uniform. Its temperature is almost the same in every direction, differing by only a few parts in 100,000. This uniformity is surprising. Regions of the universe that are now widely separated, so far apart that light has not had time to travel between them since the beginning of cosmic expansion, still share nearly identical properties. This is known as the horizon problem. How could these distant regions have coordinated their conditions if they were never in contact? There is also the flatness problem. Measurements of the universe suggest that its geometry is very close to flat, meaning that the total energy density is extremely close to a critical value. If the universe had started with even a slightly different density, it would have either collapsed back on itself or expanded too rapidly for structure to form. The fact that it sits so close to this critical balance seems, at first glance, almost too precise. Inflation offers a solution to both of these problems. It proposes that in the earliest fraction of a second, the universe underwent a period of extremely rapid expansion. During this phase, the size of the universe increased by an enormous factor, often described as growing by at least one factor of 10 raised to the power of 26 in a tiny fraction of a second. Before this expansion, the universe would have been much smaller, and regions that are now far apart would have been close enough to interact and come into thermal equilibrium. Then, inflation stretched this small, uniform region to cosmic scales, smoothing out any irregularities and producing the large, uniform universe we observe today. It is a little like taking a small, crumpled patch of fabric and pulling it tight. As you stretch it, the wrinkles become less noticeable, and the surface appears smoother. But inflation does more than just smooth the universe. It also provides a mechanism for creating the tiny variations that eventually grew into galaxies, stars, and planets. This is where quantum fluctuations come into play. At very small scales, quantum mechanics tells us that fields are never perfectly uniform. Even in a vacuum, there are constant tiny fluctuations in energy. These fluctuations are normally confined to microscopic scales, appearing and disappearing almost instantly. But during inflation, something remarkable happens. As space expands rapidly, these quantum fluctuations are stretched to much larger scales. What begins as a tiny variation in a quantum field becomes a slight difference in density across regions of space. Once inflation ends, these variations remain imprinted in the structure of the universe. Over time, gravity amplifies them. Regions that are slightly denser attract more matter, growing into the seeds of galaxies and clusters. Less dense regions become vast cosmic voids. So the large-scale structure of the universe, including the distribution of galaxies across billions of light years, can be traced back to quantum fluctuations that occurred in an incredibly brief moment during inflation. This connection between the smallest scales and the largest structures is one of the most striking features of modern cosmology, and it is supported by observations. The Planck satellite, operated by the European Space Agency, has mapped the cosmic microwave background with extraordinary precision. Its measurements reveal tiny temperature variations that match the patterns predicted by inflationary models. These variations are not random. They follow a specific statistical distribution consistent with quantum fluctuations stretched by rapid expansion. The data provides strong evidence that something very much like inflation took place. Of course, there are still open questions. We do not yet know exactly what caused inflation, or what field or mechanism drove this rapid expansion. In many models, inflation is associated with a hypothetical field known as the inflaton field, which carries a form of energy that can drive accelerated expansion. But the precise nature of this field remains uncertain, and this uncertainty leads to an even more intriguing possibility. In some versions of inflation, particularly those developed by André Linde, the process does not end everywhere at once. Instead, inflation may continue in some regions of space, even as it ends in others. This idea is known as eternal inflation. In this picture, the universe is not a single uniform entity, but a vast and continually expanding system in which new regions are constantly forming. Each region, sometimes called a bubble universe, can have its own properties, its own physical conditions, and its own history. Our observable universe would then be just one of many such regions, a small part of a much larger and more complex structure. Eternal inflation transforms the way we think about beginnings. If inflation is ongoing in some parts of the cosmos, then the process that gave rise to our universe may not be unique. It may be part of a larger self-reproducing system. And this brings us back, in a quiet way, to the question of what came before the Big Bang. If inflation can generate new regions of space, each with its own expanding universe, then the Big Bang we observe might not be the absolute beginning. It could be the beginning of our local region, emerging from a broader context that extends beyond what we can see. In this sense, inflation does not directly answer the question of what came before, but it reshapes it. It suggests that what we call the Big Bang may be one event in a much larger process, one that may not have a single starting point, and it invites us to consider a universe that is not defined by a single origin, but by ongoing creation, a universe where new regions are constantly forming, each with its own beginning, while the larger structure continues to evolve. There is something quietly humbling about this idea. The observable universe, vast as it is, may be just one small part of a much larger reality. And the moment we think of as the beginning may be more like a local starting point rather than a universal one. So inflation, which began as a solution to specific problems in cosmology, becomes something more. It becomes a bridge between the familiar story of the Big Bang and a deeper, more expansive picture of the cosmos, where beginnings may not be singular events, but part of an ongoing unfolding process. And as we follow that bridge further, the question begins to open again, not as a simple request for an earlier moment, but as an invitation to explore the wider landscape in which our universe may be just one quiet part. If we follow the logic of inflation a little further, and then step gently into the world of quantum physics, the idea of a beginning begins to shift once again. Because at the smaller scales, reality behaves in a way that is very different from our everyday experience. In quantum mechanics, emptiness is not truly empty. Even what we call a vacuum, a region of space with no particles, is not a quiet, featureless void. Instead, it is filled with activity at the smallest scales. Fields fluctuate, energy appears and disappears, pairs of particles can briefly come into existence and then vanish again, all within incredibly short intervals. These are known as quantum vacuum fluctuations. They arise from one of the central principles of quantum mechanics, the uncertainty principle, introduced by Werner Heisenberg. This principle states that certain pairs of physical quantities cannot both be known with perfect precision at the same time. In one common form, it can be expressed as the uncertainty in energy multiplied by the uncertainty in time is greater than or equal to a constant value related to Planck's constant. In simple terms, this means that for very short periods of time, small amounts of energy can appear without violating the laws of physics, as long as they disappear quickly enough. So the vacuum is not a static emptiness. It is more like a restless sea, constantly shifting at scales far smaller than we can observe directly. In most situations, these fluctuations remain confined to microscopic distances. They flicker in and out of existence without leaving lasting traces. But under certain conditions, especially in the early universe, these fluctuations can be amplified. We have already seen how inflation can stretch quantum fluctuations to cosmic scales, turning tiny variations into the seeds of galaxies. But some physicists have taken this idea further. They have asked whether an entire universe could emerge from a quantum fluctuation. One of the key figures in this line of thought is Alexander Vilenkin. Vilenkin proposed that the universe could have originated through a process known as quantum tunneling from nothing. In quantum mechanics, tunneling refers to the ability of particles to pass through barriers that would be impossible to cross according to classical physics. It is a well-established phenomenon, observed in many systems, including nuclear decay and semiconductor devices. Vilenkin suggested that a similar process could apply to the universe as a whole. In his model, the universe begins as a quantum event, tunneling into existence from a state that does not contain space or time in the usual sense. This is sometimes described as creation from nothing, but here the word nothing requires careful attention. In everyday language, nothing usually means the complete absence of anything at all. No matter, no energy, no space, no time. In physics, however, the concept is often more subtle. When Lawrence Krauss discusses the idea of a universe emerging from nothing, he's referring to a quantum vacuum, or to a state described by physical laws, even if it does not contain particles or classical structures. This kind of nothing is not truly nothing in the philosophical sense. It is a state governed by quantum fields, mathematical rules, and underlying structures. So when we hear that the universe might arise from nothing, it is important to ask what kind of nothing is being described. Is it a complete absence of existence? Or is it a physical state that lacks certain features but still contains the potential for change? This distinction may seem subtle, but it plays a central role in how we interpret these ideas. In Vilenkin's picture, the universe does not emerge from a pre-existing space. Instead, space itself comes into existence as part of the tunneling process. There is no external time in which this event occurs. Rather, time begins as the universe begins. This is similar in spirit to the earlier idea that time may not extend beyond the Big Bang. But here, the emphasis is on quantum processes. The universe is not simply expanding from a dense state. It is appearing as a solution to the equations of quantum cosmology. This brings us to one of the most intriguing equations in this field. The Wheeler-DeWitt equation, developed by John Archibald Wheeler and Bryce DeWitt, attempts to describe the quantum state of the entire universe. Unlike the familiar equations of motion, which describe how systems evolve over time, the Wheeler-DeWitt equation does not contain time in the usual way. It is often written in a form that can be described in words as the Hamiltonian operator, acting on the wave function of the universe equals 0. The wave function of the universe, in this context, encodes all possible configurations of spacetime and matter. Instead of describing a single history, it represents a superposition of many possible states. This leads to a very different way of thinking about existence. Rather than a universe that begins at a specific moment and evolves forward, we have a quantum description in which multiple possibilities exist simultaneously, and what we observe is one realization among many. In this framework, the emergence of the universe can be understood as a transition from a quantum state to a classical one, where definite structures begin to form. The idea of a single, well-defined beginning becomes less central. Instead, the universe is described in terms of probabilities. Certain configurations are more likely than others. Certain paths are favored. But there is no single, deterministic starting point in the traditional sense. This perspective can feel quite different from the intuitive picture of a beginning. It replaces the idea of a single event with something more diffuse, a process, a transition, a shift from possibility to actuality. And it suggests that the question of what came before may not have a straightforward answer. Because if the universe is fundamentally described by a quantum state, then the notion of before may not apply in the usual way. There may not be a sequence of moments leading up to the beginning. Instead, there may be a set of conditions from which the universe emerges, not through a step-by-step progression, but through a quantum transition. This does not make the universe any less real, but it does change how we think about its origin. It moves us away from the image of a single moment of creation and toward a picture in which the universe arises from deeper principles, governed by probability, uncertainty, and the structure of quantum fields. There is something quietly remarkable about this idea. The vastness of the cosmos, with its billions of galaxies and countless stars, may trace its origin back to fluctuations at the smallest scales. Tiny variations in energy, guided by the rules of quantum mechanics, stretched and amplified by cosmic expansion, eventually giving rise to everything we see. And yet, even with this understanding, the deeper question remains open. What is the nature of the underlying state from which the universe emerges? Is it truly nothing in the philosophical sense? Or is it a rich, structured foundation described by laws that we are only beginning to understand? As we continue to explore these ideas, the question becomes less about finding a single answer and more about understanding the range of possibilities. Each perspective offers a different way of thinking about beginnings. Some suggest that the universe emerged from a quantum fluctuation. Others propose that it is one of many possible outcomes within a broader framework. And in each case, the concept of a beginning becomes a little more subtle, a little less like a moment in time, and a little more like a transition from possibility into reality, shaped by the quiet, underlying rules of the quantum world. As the idea of inflation expanded our picture of the early universe, it also opened a door to something much larger. Because if inflation can happen once, there is a natural question that follows. Could it happen more than once? Andre Linde explored this possibility in detail, developing what is now known as eternal inflation. In this model, inflation is not a single, brief event that occurred everywhere at the same time and then stopped. Instead, it is a process that continues indefinitely in some regions of space, even as it ends in others. To understand this, it helps to imagine the inflaton field, the hypothetical field responsible for driving inflation, as having a certain energy landscape. In some regions, the field settles into a lower energy state, causing inflation to end locally. When that happens, the energy stored in the field is released, reheating the region and giving rise to a hot, dense state similar to what we describe as the beginning of our observable universe. But in other regions, the field remains at higher energy levels, and inflation continues. As space expands, these inflating regions grow, and within them, new regions can again transition into lower energy states, forming new bubble universes. Each of these bubbles can evolve independently, with its own expansion, its own structure, and potentially its own physical properties. So rather than a single universe with one beginning, eternal inflation suggests a vast ongoing process in which universes are constantly being created. Our observable universe would be just one of these bubbles, a local region where inflation ended and the familiar processes of cosmic evolution began. This idea has a certain quiet elegance. It takes the mechanism that explains the early behavior of our universe and extends it naturally without requiring a special, one-time event, and it changes the way we think about beginnings. Because if new universes are continuously forming, then the Big Bang we observe may not be the beginning of everything. It may be the beginning of our particular region, within a much larger and possibly unbounded structure. This broader picture is often referred to as the multiverse. The term itself can describe several different ideas, but in this context, it refers to a collection of universes, each with its own properties, existing within a larger framework. One of the most detailed theoretical motivations for a multiverse comes from string theory. Leonard Susskind and others have explored what is known as the string landscape. In string theory, the fundamental objects are tiny vibrating strings, and the way these strings vibrate determines the properties of particles and forces. But string theory also allows for a vast number of possible solutions, each corresponding to a different way that extra dimensions can be compactified or arranged. Each solution leads to a different set of physical laws, different values for fundamental constants, different strengths for forces, different types of particles. The number of possible solutions is often described as extremely large, sometimes estimated to be on the order of 10 raised to the power of 500. This enormous range of possibilities forms what is called the landscape. If eternal inflation is real, then different bubble universes could settle into different points within this landscape, each realizing a different set of physical laws. In this picture, the multiverse is not just a collection of identical universes, it is a vast ensemble of diverse realities, each with its own characteristics. This leads to an interesting question about the nature of the constants we observe in our universe. Why do the fundamental constants, such as the strength of gravity or the mass of elementary particles, have the values that they do? Some of these values appear to be finely tuned. If they were slightly different, the universe might not be able to form stable atoms, stars, or galaxies. In some cases, even small changes could prevent the emergence of complex structures altogether. This is often referred to as the fine-tuning problem. Within a multiverse framework, one possible explanation is that many different universes exist, each with different constants. We find ourselves in one of the universes where the conditions happen to allow for the development of complexity, simply because those are the only environments in which observers can exist. This idea is sometimes associated with the anthropic principle. It does not suggest that the universe was designed for observers, but rather that observers can only arise in universes with certain properties. So our observations are naturally biased toward those conditions. Max Tegmark has explored these ideas further by proposing a classification of different types of multiverses. In his framework, there are multiple levels. At one level, the multiverse consists of regions beyond our observable horizon, still part of the same overall space-time but too far away for light to have reached us. At another level, it includes the bubble universes of eternal inflation, each potentially with different physical constants. And at even more abstract levels, Tegmark suggests that all mathematically consistent structures might correspond to physical realities, leading to a kind of mathematical multiverse. These ideas extend far beyond the original question of what came before the Big Bang. They suggest that the Big Bang itself may be a local event within a much larger and more complex system. But there is an important challenge here. Testing these ideas is difficult. Science relies on observation and experiment. It depends on the ability to make predictions that can be confirmed or refuted by data. And by definition, regions beyond our observable universe are not directly accessible. We cannot travel to other bubble universes. We cannot observe them directly, at least not with current technology or understanding. This raises questions about testability and falsifiability. How can we evaluate a theory if its predictions lie beyond what we can observe? Some physicists argue that indirect evidence may still be possible. For example, certain models of eternal inflation might leave subtle imprints in the cosmic microwave background, such as patterns that could be interpreted as collisions between bubble universes. Others suggest that the statistical properties of the constants we observe could provide clues, but these approaches are still under active investigation, and there is no consensus. So the multiverse remains a fascinating and open area of research. It is grounded in serious theoretical work, but it also pushes against the boundaries of what can be tested. And yet, even with these uncertainties, it offers a powerful shift in perspective. Instead of asking what came before the Big Bang as though it were a single moment in a single timeline, we begin to see the possibility that our universe is part of a much larger context. A context in which new regions are continually forming. A context in which beginnings are local rather than absolute. And in which the question of before may not point to a single answer, but to an entire landscape of possibilities. In this view, the Big Bang becomes less like a singular origin and more like a transition point, a boundary between phases, a moment when one region of a larger system entered into a new state of expansion and evolution. There is something quietly expansive about this idea. It does not close the question, instead it opens it outward, suggesting that what we see may be just one small part of a much larger story, one that extends beyond the limits of our observation, and perhaps even beyond the limits of our current understanding. And somewhere within that wider picture, the notion of a beginning becomes less about a single point in time, and more about the structure of the cosmos as a whole. There is another way to approach the question of what came before the Big Bang, one that feels both familiar and quietly reassuring. Instead of imagining a single beginning, we can imagine a cycle, a universe that does not begin once but many times, expanding, evolving, and then somehow returning to a state that allows the process to happen again. This idea, known broadly as cyclic cosmology, has appeared in different forms throughout the history of physics, but in modern cosmology, it has been explored in detail by scientists such as Roger Penrose, Paul Steinhardt, and Neil Turok. At its heart, the concept is simple. The universe we see today may not be the first. It may be one phase in a much longer sequence, with earlier phases stretching back into the past. But the details of how such cycles might work are anything but simple. Roger Penrose has developed one of the most distinctive versions of this idea, known as conformal cyclic cosmology. In Penrose's model, the universe evolves through a series of stages called aeons. Each aeon begins with a Big Bang-like expansion and continues for an immense period of time, during which galaxies form, stars shine, and black holes eventually dominate. Over extremely long timescales, something interesting happens. Black holes, according to Stephen Hawking's work on black hole radiation, slowly lose mass and energy through a process now known as Hawking radiation. Given enough time, even the largest black holes can evaporate completely. As the universe continues to expand, matter becomes increasingly sparse. Particles decay, structures dissolve. Eventually what remains is a very dilute, low-energy state dominated by radiation. In this state, the distinction between large and small scales begins to lose its meaning. Penrose argues that when all massive particles have decayed and only massless particles remain, the concept of scale becomes irrelevant. Without mass, there is no preferred unit of size or time. This allows the universe, in a mathematical sense, to be rescaled. The very large can be mapped onto the very small, and in this rescaled picture, the end of one aeon can be smoothly connected to the beginning of the next. So the Big Bang of our universe could correspond to the infinitely expanded, extremely dilute state of a previous ion. In this view, there is no single beginning. There is an ongoing sequence, where each cycle emerges naturally from the one before it. It is a subtle and elegant idea. Instead of a sharp boundary, there is a kind of continuity, where endings become beginnings through a change in perspective. Paul Steinhardt and Neil Turok have explored a different type of cyclic model, often referred to as the ekpyrotic universe. In their framework, the cycles are driven by interactions in higher dimensional space, sometimes involving structures known as branes, which come from string theory. In this picture, our universe exists on a three-dimensional brane, embedded within a higher dimensional space. Periodically, this brane may collide with another, releasing energy and triggering a new phase of expansion. Each collision acts like a reset, initiating conditions similar to those of a Big Bang. Between these collisions, the universe evolves, expands, and cools, before eventually returning to a state that allows the next cycle to occur. These models differ in their details, but they share a common theme. The universe may have a history that extends beyond the Big Bang. It may not have a single origin, but rather a repeating pattern. Alongside these cyclic ideas, there are also models that focus on a single transition, rather than an endless sequence. These are often referred to as bounce models. In a bounce scenario, the universe begins in a contracting phase. Over time, gravity pulls matter inward, increasing the density and temperature. But instead of collapsing into a singularity, something prevents the collapse from reaching infinite density. At some minimum scale, the contraction stops and reverses. The universe begins to expand again. This transition from contraction to expansion is known as a bounce. Loop quantum gravity provides one framework in which such a bounce can occur. In this theory, space-time is quantized, meaning it has a discrete structure at the smallest scales. As the universe contracts and density increases, quantum effects become significant. These effects can produce a form of repulsive gravity under extreme conditions, preventing the formation of a singularity. Abhay Ashtekar and others have developed models in which the classical Big Bang singularity is replaced by a quantum bounce. In these models, the universe before the Big Bang is not empty or undefined. It is a prior phase of contraction. The expansion we observe today is simply the continuation of a process that has passed through a minimum point. Nikita Poplawski has explored a related idea using a theory known as Einstein-Cartan gravity. In this framework, spacetime includes a property called torsion, which is related to the intrinsic spin of particles. At very high densities, torsion can produce effects that counteract gravitational collapse. This can also lead to a bounce, where the universe avoids a singularity and transitions from contraction to expansion. Interestingly, Poplawski has suggested that such bounces could occur inside black holes, potentially giving rise to new universes. This idea links bounce cosmology with the earlier notion that black holes might be seeds for new cosmic regions. When we compare cyclic models and bounce models, there are both similarities and differences. Both avoid the idea of a singular beginning. Both suggest that the universe has a history that extends beyond the Big Bang. But cyclic models often involve repeated sequences, where the universe goes through many phases over time, while bounce models typically focus on a single transition from a prior state. Cyclic models emphasize continuity across vast timescales. Bounce models emphasize the resolution of singularities through quantum effects. In both cases, the Big Bang becomes something different from what we might have first imagined. It is no longer the absolute beginning of everything. It is a transition point, a moment where the universe changes direction, or where one phase gives way to another. This shift in perspective can feel quite gentle. Instead of imagining a universe that suddenly appears from nothing, we begin to see a universe that evolves through different states, each connected to the next. There is something almost rhythmic about it: expansion and contraction, emergence and transformation. A sequence that may extend far beyond what we can observe. Of course, these ideas are still under active investigation. There is ongoing debate about whether cyclic or bounce models can fully account for the observations we have, including the detailed structure of the cosmic microwave background and the distribution of galaxies. Some models face challenges related to entropy, which tends to increase over time, potentially making it difficult to maintain consistent cycles. Others are still being developed, with new mathematical tools and simulations helping to refine their predictions. So while these ideas are compelling, they are not yet confirmed. But they offer something valuable. They show that the concept of a beginning is not fixed. It depends on the framework we use to describe the universe. And in some frameworks, the idea of a single, absolute beginning gives way to something more continuous. A universe that has a past. A universe that changes form. A universe where what we call the beginning may simply be one moment in a much longer story. And as we consider these possibilities, the question we started with begins to feel a little different. Not just what came before the Big Bang, but whether the Big Bang itself is part of a larger cycle, one that quietly extends beyond the limits of our current view. There is a way of looking at the universe that gently shifts the stage on which everything takes place. Instead of imagining all of reality confined to the 3 dimensions of space and one of time that we experience, some theories suggest that the universe may be part of something larger, something with additional dimensions. These extra dimensions are not directions we can easily point to, like left or right, up or down. They may be hidden, compact, or structured in ways that are not directly accessible to our senses. But within certain theoretical frameworks, they play a central role. One of the most developed of these frameworks is string theory. In its modern form, shaped by contributions from physicists such as Edward Witten, string theory proposes that the fundamental building blocks of the universe are not point-like particles, but tiny vibrating strings. Each string can oscillate in different ways, and each pattern of vibration corresponds to a different particle. An electron is one pattern, a quark is another. A photon, which carries light, is yet another. This idea allows for a unified description of all known particles and forces, including gravity, which is traditionally difficult to incorporate into quantum theory. But for string theory to work mathematically, it requires more dimensions than the 4 we are familiar with. In many versions, the universe contains 10 or 11 dimensions, depending on the specific formulation. The additional dimensions are thought to be compactified, meaning they are curled up into extremely small shapes, perhaps on the scale of 10 raised to the power of -35 meters. At such scales, they would be far beyond direct observation, which is why we do not notice them in everyday life. Even though these dimensions are hidden, they may influence the behavior of particles and the structure of the universe. This leads to a fascinating possibility. What we perceive as our universe may be just a lower dimensional slice of a higher dimensional reality. In some models, this idea is developed further through what is known as brane cosmology. The term brane comes from the word membrane, and it refers to a multidimensional surface embedded within a higher dimensional space, often called the bulk. In this picture, our universe could be a 3-dimensional brane floating within a higher dimensional bulk. All the particles and forces we observe, except possibly gravity, are confined to this brane. Gravity, however, may be able to propagate into the extra dimensions, which could help explain why it appears so much weaker than the other fundamental forces. If this framework is correct, then events that occur in the higher dimensional bulk could influence what happens in our universe. And this brings us to a very different way of thinking about the Big Bang. Instead of being the absolute beginning of everything, it could be the result of an interaction in a higher dimensional space. Paul Steinhardt and Neil Turok have explored this idea through the ekpyrotic universe model. In this scenario, our brane exists alongside another brane within the higher dimensional bulk. Over time, these branes can move relative to each other. Eventually, they may collide. This collision releases a tremendous amount of energy, heating the branes and triggering a phase of expansion that resembles the Big Bang. After the collision, the branes move apart again, and the universe evolves, forming matter, radiation, and structure. In this view, the Big Bang is not the beginning of space and time. It is the result of a physical event, a collision between higher dimensional objects, and if such collisions can happen more than once, then the process could repeat, leading to a cyclic pattern. This idea connects naturally with earlier discussions of cyclic cosmology, but it places the mechanism in a higher dimensional context. Another approach within string theory comes from Gabriele Veneziano, who developed what is known as pre-Big Bang string cosmology. In this model, the universe exists in a different phase before the Big Bang, characterized by a contracting state driven by the dynamics of string theory. Instead of starting from a singular point, the universe evolves from a prior configuration in which the fundamental fields behave differently. As the universe contracts, certain quantities grow, eventually leading to a transition into the expanding phase we observe. This transition replaces the classical singularity with a more complex process governed by string dynamics. So once again, the Big Bang becomes a transition rather than a beginning. It marks a change in the behavior of the universe, rather than the creation of everything from nothing. Across these models, a common theme begins to emerge. The question of what came before the Big Bang may not refer to an earlier moment in time within our universe. Instead, it may point to events that take place outside the dimensions we directly experience. If the universe is embedded in a higher dimensional space, then the origin of our observable reality could lie in that larger structure. The Big Bang could be a boundary between different phases, or the result of interactions that occur beyond our familiar space-time. This idea can feel quite abstract. After all, it is difficult to imagine dimensions beyond those we can perceive. But mathematics provides a way to explore these possibilities, and string theory offers a consistent framework in which they can be described. Of course, these ideas remain speculative. There is currently no direct experimental evidence for extra dimensions or brane collisions. Efforts to detect signs of extra dimensions, such as deviations in gravitational behavior at small scales or signatures in high-energy particle collisions, have not yet produced definitive results. But the absence of evidence is not necessarily evidence of absence. It simply means that if extra dimensions exist, they are either too small or too subtle to detect with current technology. Still, these models offer something valuable. They expand the range of possibilities. They remind us that the universe we observe may not be the whole of reality but part of a larger structure. And they provide a framework in which the question of what came before the Big Bang can be reinterpreted. Not as a question about an earlier time within our universe, but as a question about the deeper processes that give rise to our universe in the first place. In this view, the Big Bang is not an isolated event. It is connected to a broader context, one that may involve additional dimensions, hidden structures, and interactions beyond our direct observation. There is something quietly intriguing about this perspective. It suggests that the story of the universe may extend beyond the boundaries we can see, that what appears to be a beginning may be part of a larger process unfolding in a space we do not directly experience. And as we continue to explore these ideas, the question begins to shift once again. Not just what came before the Big Bang, but where that before might exist, perhaps not in time as we know it, but in dimensions that lie just beyond the reach of our senses, shaping the universe in ways we're only beginning to understand. There is a place in the universe where our understanding of physics becomes as strained as it does at the beginning of time, a place where gravity is so strong that not even light can escape, a place where space and time themselves are pushed to their limits. These are black holes. At first glance, black holes might seem like endpoints, regions where matter collapses inward, disappearing from view, leaving behind only a boundary known as the event horizon. But some physicists have wondered whether they might be something more, not just endings, but beginnings. Lee Smolin introduced an idea known as cosmological natural selection, which brings a rather unusual perspective to this possibility. In Smolin's proposal, universes can reproduce. The mechanism for this reproduction is black holes. When a massive star collapses under its own gravity, it can form a black hole. Inside that black hole, according to classical general relativity, matter is compressed toward a singularity, a point of infinite density where the known laws of physics break down. But as we have seen before, singularities are often signs that our theories are incomplete. So Smolin considered what might happen if quantum effects prevent the formation of a true singularity. Instead of collapsing into an infinitely dense point, the matter inside a black hole might reach a maximum density and then transition into a new expanding region of space-time. In other words, the interior of a black hole could give rise to a new universe. This new universe would be causally disconnected from the original one. Observers outside the black hole would never see it form, because information cannot escape from within the event horizon. But from the perspective of the new universe, it would appear as though it began with something very much like a Big Bang. This leads to a remarkable possibility. Each black hole in our universe could be the seed of a new universe, and each of those universes could, in turn, form black holes of their own, continuing the process. In Smolin's model, this creates a kind of cosmic evolution. Universes that produce more black holes have more offspring, so over many generations the properties of universes might shift toward those that favour black hole formation. This is why the idea is called cosmological natural selection. It draws an analogy with biological evolution, where traits that enhance reproduction become more common over time. Of course, this is not evolution in the biological sense. There are no organisms, no genes, and no conscious selection. But the underlying principle is similar. Certain properties lead to more replication, and over time, those properties become more prevalent. This idea connects naturally with the earlier discussion of the multiverse. Instead of universes forming randomly through quantum fluctuations or eternal inflation, they could also arise through the life cycle of stars and black holes. Each universe would be linked to others through a chain of formation events, even if those links are hidden from direct observation. But for this picture to work, one key challenge must be addressed: the singularity. In classical general relativity, the interior of a black hole leads inevitably to a singularity, where density becomes infinite and the equations break down. If this singularity is a real physical endpoint, then there is no room for a new universe to emerge, so alternative descriptions are needed. This is where quantum gravity enters the picture once again. In some approaches, including loop quantum gravity, the extreme conditions inside a black hole could trigger quantum effects that prevent the formation of a singularity. Instead of collapsing indefinitely, spacetime could reach a minimum scale and then undergo a transition. A bounce. This bounce could connect the interior of the black hole to a new expanding region of spacetime. From the outside, the black hole appears as a compact object with a finite lifetime, slowly losing mass through Hawking radiation. But on the inside, it could be the origin of an entirely new universe. Nikita Poplawski has explored a related idea using Einstein-Cartan theory, which includes torsion as a property of spacetime. In this framework, the intrinsic spin of particles contributes to the geometry of spacetime, especially at very high densities. Torsion can generate a repulsive effect that counteracts gravitational collapse, preventing the formation of a singularity. This allows for a scenario in which matter inside a black hole reaches a maximum density and then expands into a new universe. In this view, black holes are not endpoints at all, they are bridges. Each one connects one universe to another. This raises an intriguing question. If black holes can create new universes, could our own universe have formed in this way? Could the Big Bang we observe be the result of a collapse that occurred inside a black hole in a parent universe? It is a speculative idea, but it fits naturally within the framework of these models. From our perspective, the Big Bang appears as a beginning, but from the perspective of the parent universe, it could be the continuation of a process, the formation of a black hole leading to a new region of spacetime. In this sense, the question of what came before the Big Bang takes on a different meaning. It may not refer to an earlier time within our universe, but to a different universe entirely. One that we cannot observe directly, one that exists outside our causal horizon, and yet, one that may be connected to us through the deepest structure of spacetime. There is something quietly compelling about this idea. It transforms black holes from mysterious endpoints into generative processes. It suggests that the universe is not a single, isolated system, but part of a larger network of connected regions, each giving rise to the next, and it offers a different kind of answer to the question of origins. Not a single beginning, but a lineage, a sequence of universes, each emerging from the collapse of matter in another. Of course, as with many of the ideas we have explored, this remains an area of active research. There is no direct observational evidence that black holes create new universes, and testing such a hypothesis presents significant challenges, since any new universe would be hidden behind an event horizon. But the idea is grounded in serious attempts to reconcile general relativity with quantum mechanics, and it provides a coherent framework in which singularities are replaced by transitions. It also highlights a broader theme. The boundaries we encounter in physics, whether at the beginning of the universe or inside a black hole, often point to deeper structures. They suggest that what appears to be an endpoint may actually be a doorway. And in that sense, black holes and the Big Bang may not be so different after all. Both mark regions where our current theories reach their limits. Both involve extreme conditions where spacetime behaves in unfamiliar ways, and both may be connected to processes that extend beyond what we can directly observe. So as we continue to explore the question of what came before the Big Bang, it is worth considering that the answer might not lie in a single moment in time. It might lie in a different universe, a parent universe, one that gave rise to our own through a process that is still, quietly, unfolding across the cosmos. There is a different way to think about the universe, one that moves gently away from the idea of matter as the most fundamental ingredient of reality. Instead of asking what things are made of, it asks something slightly more abstract. What if, at the deepest level, the universe is made of information? This idea was explored by John Archibald Wheeler, a physicist who had a talent for expressing complex concepts in simple, memorable phrases. He described his perspective with the phrase, "it from bit." By this, Wheeler meant that every physical entity, every particle, every field, every structure in the universe ultimately arises from bits of information. A bit is the simplest unit of information. It represents a choice between two possibilities, such as yes or no, 0 or 1. Wheeler's proposal suggests that physical reality emerges from answers to fundamental questions, from the outcomes of interactions that can be understood as informational events. It is a subtle shift. Instead of matter being primary and information describing it, information becomes primary and matter emerges from it. At first, this might sound like a philosophical idea rather than a scientific one, but there are strong connections between information and physics. Rolf Landauer, a physicist working at IBM, demonstrated that information is not abstract in the way we might assume. It has physical consequences. Landauer's principle states that erasing information requires energy and produces heat. In simple terms, when a bit of information is reset, the process has a measurable effect on the physical world. This connects information directly to thermodynamics. It shows that information is not separate from physical reality, but deeply embedded within it. Every computation, every change in a system has a physical cost. Building on these ideas, Seth Lloyd has proposed that the universe itself can be understood as a quantum computer. In this view, the universe processes information through its physical interactions. Every particle interaction, every quantum transition, every exchange of energy can be seen as a computational step. The universe, in effect, is continuously calculating its own evolution. Lloyd has even attempted to estimate how much computation the universe has performed since its early moments. Based on the total amount of energy in the age of the universe, he suggests that the number of operations could be on the order of 10 raised to the power of 120. This is an unimaginably large number, far beyond anything we encounter in everyday experience. But it provides a sense of scale. The universe is not just vast in space, it is vast in computation. This perspective leads to an interesting possibility. If the universe is fundamentally informational, then the structures we observe, including space, time, and matter, may emerge from patterns of information processing. Instead of thinking of the universe as a collection of objects moving through space, we might think of it as a network of interactions, where information is exchanged, transformed, and organized. This connects naturally with earlier ideas about quantum fluctuations and the emergence of structure. Quantum states can be described in terms of information. The probabilities, the superpositions, the correlations between particles all reflect the way information is distributed and evolves. Entropy, which we encountered when discussing the arrow of time, can also be understood in informational terms. In thermodynamics, entropy measures the number of possible microscopic configurations that correspond to a given macroscopic state. In information theory, entropy measures uncertainty, or the amount of information needed to describe a system. These two definitions are closely related. In fact, the entropy of a physical system can be interpreted as a measure of how much information is hidden in its microscopic details. So as the universe evolves and entropy increases, the informational structure of the universe changes. The distribution of information becomes more complex, more spread out, and more difficult to compress into simple descriptions. This suggests that the flow of time itself may be linked to the processing of information. As systems evolve, they transform information, and this transformation gives rise to the experience of change. So where does this leave the question of what came before the Big Bang? If we adopt an informational perspective, the question may need to be reframed once again. Instead of asking what physical state existed before the Big Bang, we might ask what informational structure gave rise to the universe. Was there a prior configuration of information, a deeper level of description from which space-time and matter emerged? Or is the concept of before tied so closely to time that it loses meaning when applied to an informational foundation? In some approaches to quantum gravity, space-time itself is thought to emerge from patterns of entanglement, a uniquely quantum form of correlation between systems. Entanglement describes how the state of one particle can be linked to the state of another, even across large distances. These correlations can be seen as connections in an informational network. Some researchers have suggested that the geometry of space-time, including distances and curvature, may arise from the structure of these connections. If this is the case, then space is not a background in which information exists. It is a consequence of how information is organized, and time, similarly, may emerge from the way information changes. In this picture, the Big Bang is not simply a physical event. It is a transition in the informational structure of the universe, a point at which a certain configuration gives rise to the familiar patterns of space-time, matter, and energy. What came before that transition may not be a physical state in the usual sense. It may be an informational state, one that does not have space or time as we understand them. This idea can feel quite abstract. but it offers a way to think about origins that does not rely on a classical notion of a beginning in time. Instead, it suggests that reality may be built from deeper layers, where information is the fundamental ingredient. And from that foundation, the universe emerges, not as a single event, but as a process of organization, a process of computation, a process in which simple informational elements combine and evolve into the rich, structured cosmos we observe. There is something quietly elegant about this perspective. It replaces the question of what came before with a different kind of curiosity, not about an earlier moment, but about the underlying rules that govern how information is structured and transformed. And in that sense, the origin of the universe becomes less about a specific point in time, and more about the deeper patterns that make time itself possible. There is a quietly surprising idea in modern physics that invites us to rethink what we mean by space itself. It suggests that everything we experience in 3 dimensions, every distance, every direction, every structure, may not be fundamental. Instead, it may be encoded on a surface with fewer dimensions. This idea is known as the holographic principle. It was first proposed in the 1990s by Gerard 't Hooft, and later developed in detail by Leonard Susskind. The inspiration came, in part, from the study of black holes. When physicists examined the properties of black holes, they found something unexpected about entropy, which, as we have seen, is closely related to information. The entropy of a black hole, as described by Jacob Bekenstein and Stephen Hawking, is not proportional to its volume, as one might expect, but to the area of its event horizon. This relationship can be expressed in words as the entropy of a black hole equals a constant multiplied by the area of its event horizon, divided by 4 times the Planck area. This result suggests that the maximum amount of information contained within a region of space is determined not by its volume, but by the area of its boundary. In other words, all the information about what is inside a region can be encoded on its surface. This is a deeply counterintuitive idea. We are used to thinking of 3-dimensional objects as requiring 3-dimensional descriptions. A room, for example, feels like it contains information throughout its volume. But the holographic principle suggests that, at a fundamental level, the complete description of that room could be stored on its walls. It is a bit like a hologram. In a holographic image, a 2-dimensional surface can encode all the information needed to produce a 3-dimensional image when illuminated in the right way. The image appears to have depth, even though the information is contained on a flat surface. The holographic principle extends this idea to the universe itself. It suggests that the 3-dimensional world we experience may be a projection of information encoded on a lower dimensional boundary. This idea became more concrete with the work of Juan Maldacena in the late 1990s. Maldacena developed a framework known as the anti-de Sitter conformal field theory correspondence, often abbreviated as ADSCFT. In this correspondence, a gravitational theory in a higher dimensional space is mathematically equivalent to a quantum field theory defined on its lower dimensional boundary. The 2 descriptions are different, but they contain the same information. Events in the higher dimensional bulk space can be fully described by processes on the boundary. This duality provides a powerful tool for studying complex systems, because it allows physicists to translate problems in one framework into more manageable problems in another. But it also carries a profound implication. If such a correspondence applies more generally, then the universe we experience, with its familiar dimensions and gravitational dynamics, could be equivalent to a description that exists on a lower dimensional boundary. In that case, space itself may not be fundamental. It may emerge from the way information is organized on that boundary. This leads to a different way of thinking about origins. If the universe is a projection of information from a boundary, then the question of what came before the Big Bang may not refer to an earlier moment in time within the bulk. Instead, it may relate to the conditions on the boundary. The Big Bang could be understood as a feature of how the boundary encodes information, rather than as a singular event occurring within spacetime. In this picture, the origin of the universe becomes a question about encoding, about how information is arranged, how it evolves, and how it gives rise to the appearance of space, time, and physical processes. There is something quietly elegant about this idea. It suggests that the complexity of the universe, with its vast structures and intricate dynamics, may arise from simpler underlying rules. Rules that operate on a surface, rather than throughout a volume. And it offers a way to think about the Big Bang that does not require a traditional beginning. Instead of a moment where everything starts, we have a condition, a configuration of information that gives rise to the universe as we observe it. The notion of before then becomes less straightforward. If space-time itself is emergent, then asking what came before it may be like asking what lies outside the image projected by a hologram. The answer does not exist within the same framework. It lies in the underlying structure that produces the projection. This does not mean that the question is meaningless, but it does suggest that the answer may not take the form we expect. Rather than pointing to an earlier time, it may point to a deeper level of description, a level where space and time are not yet defined, and where the fundamental ingredients are patterns of information on a boundary. Of course, the holographic principle is still an active area of research. While the ADS-CFT correspondence is well established within certain mathematical contexts, it is not yet clear how directly it applies to our universe, which does not appear to have the exact properties of anti-de Sitter space. Physicists continue to explore whether similar dualities can be extended to more realistic cosmological settings. There are ongoing efforts to understand how space-time geometry might emerge from entanglement, how information is distributed across boundaries, and how these ideas connect with observations. So while the holographic principle is not yet a complete description of reality, it offers a compelling perspective. It challenges our assumptions about space, about dimensionality, and about what it means for something to exist. And it provides another way to approach the question we have been following, not by looking further back in time, but by looking beneath time itself, toward a level where the universe is not a stage on which events unfold, but a structure that emerges from deeper patterns. In that sense, the Big Bang becomes less like the beginning of a story, and more like the moment when the story becomes visible. There is a quiet direction built into the universe. We experience it constantly, though we rarely pause to notice it. A cup of hot tea cools down as it sits on a table. Ice melts into water, but water does not spontaneously freeze into a perfect cube on a warm afternoon. Memories are formed of the past, not the future. All of these familiar experiences share something in common. They have a direction, and that direction is closely tied to a concept known as entropy. Entropy is a central idea in thermodynamics, the branch of physics that deals with heat, energy, and the behavior of systems with many particles. At its core, entropy measures the number of ways a system can be arranged at a microscopic level, while still appearing the same at a larger scale. A simple way to think about this is through order and disorder. A neatly arranged deck of cards has low entropy. There are relatively few ways to arrange the cards while keeping them in perfect order. A shuffled deck, on the other hand, has high entropy. There are an enormous number of possible arrangements that all look equally random. In physical systems, higher entropy corresponds to greater disorder, or more precisely, to a larger number of possible microscopic configurations. The second law of thermodynamics states that in an isolated system, entropy tends to increase over time. This does not mean that entropy must increase in every small step, but overall, systems evolve from states of lower entropy to states of higher entropy. This law is remarkably consistent across a wide range of phenomena. It governs the flow of heat, the mixing of substances, and the behavior of complex systems, and it provides a foundation for what is known as the arrow of time. Ludwig Boltzmann, a physicist working in the 19th century, played a key role in connecting entropy with the direction of time. He showed that the tendency for entropy to increase arises from probability. There are simply more ways for a system to be disordered than ordered. So over time, systems naturally evolve towards states that are more probable, which correspond to higher entropy. This gives time a direction. We move from less probable states to more probable ones, from order to disorder, from low entropy to high entropy. This direction is deeply embedded in our experience. It is why we remember the past but not the future. It is why causes precede effects. It is why processes unfold in a particular sequence. But when we apply this idea to the universe as a whole, something interesting appears. The early universe shortly after the Big Bang was in a state of very low entropy. This may seem surprising at first. After all, the early universe was extremely hot and dense, which might suggest a high level of disorder. But entropy is not just about temperature or density. It is about the number of possible configurations. In the early universe, matter and energy were distributed in a very uniform way. There were no galaxies, no stars, No large-scale structures. Everything was spread out almost evenly. This uniformity corresponds to a low-entropy state in a gravitational system. Gravity tends to pull matter together, forming clumps and structures. As these structures develop, the number of possible configurations increases and entropy rises. So the early universe, smooth and nearly uniform, had low gravitational entropy. As the universe evolved, small variations grew, structures formed, and entropy increased. This progression from a low entropy beginning to a higher entropy present is what gives time its direction on a cosmic scale. But this raises an important question. Why did the universe begin in such a low entropy state? This question is still open. It is one of the deep puzzles in cosmology. Some models, including certain versions of inflation, attempt to explain how a low entropy state could arise naturally. Others suggest that the low entropy beginning may be a fundamental condition, something that simply is, rather than something derived from deeper principles. When we consider cyclic or eternal models of the universe, entropy becomes even more significant. In a cyclic universe, where the cosmos goes through repeated phases of expansion and contraction, entropy would tend to increase with each cycle. Over time, this could lead to a buildup of entropy, making each successive cycle more disordered than the last. This presents a challenge. How can a cyclic model maintain consistent conditions if entropy keeps increasing? Some proposals attempt to address this. For example, in Roger Penrose's conformal cyclic cosmology, the idea is that at extremely late times, when the universe becomes very dilute and only massless particles remain, the concept of scale loses its meaning. This allows the high entropy state at the end of one cycle to be reinterpreted as a low entropy state at the beginning of the next. It is a subtle argument, but it offers a way to reconcile cyclic behavior with the second law of thermodynamics. Other models explore mechanisms that could reset or redistribute entropy between cycles. But these ideas are still under investigation, and the role of entropy remains a central challenge. There is also a deeper connection between entropy and our perception of time. Our experience of time's flow is closely tied to the increase of entropy. We remember the past because it corresponds to states of lower entropy, where information is more structured and accessible. The future, with its higher entropy, contains more possible configurations and less definite structure. This asymmetry shapes how we perceive events. It gives rise to the sense that time moves forward. But if entropy defines the arrow of time, then what happens as we approach the beginning of the universe? If the early universe is a low entropy state, then the direction of time as we experience it points away from that state. Time flows from the Big Bang toward increasing entropy, so in a sense the Big Bang is not just a point in time, it is the origin of the arrow of time itself. And this has an interesting implication. If the arrow of time is defined by increasing entropy, then extending time backward beyond the Big Bang may not be straightforward. The direction we associate with before may not exist in the same way. In some models, time may not extend beyond the Big Bang at all. In others, it may exist, but with a different structure, possibly with entropy behaving differently. This brings us back to the question we have been exploring. What came before the Big Bang? If time is defined by the increase of entropy, and if the Big Bang represents a state of extremely low entropy, then the concept of before may not be meaningful in the usual sense. It is not just that we lack information about earlier moments. It may be that the framework we use to describe time does not apply. Instead of a timeline extending indefinitely into the past, we may have a boundary, a point where the direction of time is defined, rather than something that can be extended beyond. This does not mean that there is nothing beyond the Big Bang. It means that the language of before and after, of earlier and later, may not capture what lies at that boundary. The universe, in its earliest state, may not fit into the familiar pattern of time flowing from past to future. And as we continue to explore these ideas, the role of entropy remains central. It shapes the direction of time, it influences the evolution of the universe, and it reminds us that the flow of time, which feels so natural and constant, is deeply connected to the underlying structure of physical reality, a structure that, at its most fundamental level, may not behave in quite the way we expect. As we move deeper into the question of what came before the Big Bang, a quiet pattern begins to emerge. Again and again we reach a boundary, a place where our current theories, however successful they may be, begin to lose their clarity. and at that boundary, something interesting happens. Instead of a single answer, we find a landscape of possibilities, different approaches, different interpretations, different ways of trying to bring together the two pillars of modern physics, general relativity and quantum mechanics. This is the challenge of quantum gravity, and while some frameworks like string theory and loop quantum gravity tend to receive the most attention, there are many other ideas that explore this territory from different angles. One such idea comes from Eric Verlinde, who has proposed a concept known as emergent gravity. In Verlinde's view, gravity may not be a fundamental force at all. Instead, it could be an emergent phenomenon, arising from the statistical behavior of microscopic degrees of freedom, much like temperature emerges from the motion of molecules. To understand this, it helps to recall that gravity, in general relativity, is described as the curvature of space-time. Mass and energy tell space-time how to curve, and curved space-time tells matter how to move. Verlinde suggests that this geometric description might itself be a higher-level approximation, emerging from a deeper layer of physics that is fundamentally informational. In his framework, gravity arises from changes in entropy. When matter is present, it affects the distribution of information in space, and the resulting changes in entropy produce a force that we interpret as gravity. This idea connects with earlier discussions of information and entropy, and it offers a different route toward understanding gravity at a fundamental level. If gravity is emergent, then the structure of space-time, and perhaps even the expansion of the universe, could also emerge from underlying informational processes. Another approach comes from Laurent Friedel and others working on spin foam models. These models are closely related to loop quantum gravity, but they provide a way to describe how space-time evolves at the quantum level. In a spin foam model, space-time is not a smooth, continuous fabric. Instead, it is composed of discrete elements, connected in a network that evolves over what we perceive as time. The term spin foam refers to a structure that can be imagined as a collection of interconnected surfaces, where each element represents a quantum state of geometry. These structures encode information about areas, volumes, and the relationships between different regions of space. As the spin foam evolves, it gives rise to the appearance of a continuous space-time at larger scales. This approach offers a way to bridge the gap between the discrete nature of quantum mechanics and the smooth geometry of general relativity. It suggests that space-time itself may be built from more fundamental building blocks, with continuity emerging as an approximation. But not all physicists are convinced that current approaches are on the right track. Sabine Hossenfelder, a theoretical physicist known for her careful critiques, has raised concerns about the direction of research in quantum gravity. She has pointed out that many theories, particularly those involving extra dimensions or highly abstract mathematical structures, have yet to produce testable predictions. In her view, the lack of experimental evidence and the increasing complexity of some models may indicate that new approaches are needed. Her work highlights an important aspect of scientific progress. Theories must eventually connect with observation. They must make predictions that can be tested, refined, or potentially ruled out. Without that connection, it becomes difficult to distinguish between different possibilities. This does not mean that current theories are incorrect. It means that the field is still in an exploratory phase, and that exploration involves a diversity of ideas. Some focus on geometry, some on information, some on discrete structures, others on entirely new ways of thinking about space, time, and matter. There is no single, unified theory of quantum gravity that has been confirmed by experiment, and that is both a challenge and an opportunity. It means that when we ask what came before the Big Bang, we're not working within a completed framework. We are exploring possibilities. Each approach offers a different perspective on the nature of reality. Some suggest that space-time emerges from information, others that it is built from discrete elements, others still that it is part of a higher dimensional structure, and in each case, the concept of a beginning is treated differently. In some models, the Big Bang is replaced by a transition or a bounce. In others, it is a feature of how information is encoded. In still others, it may be an emergent phenomenon arising from deeper processes. What unites these ideas is a recognition that our current understanding is incomplete. The boundary we encounter at the beginning of the universe is not just a lack of data. It is a sign that the concepts we are using may need to be extended or revised. There is something quietly reassuring about this. Science does not require immediate answers. It moves forward by exploring, questioning, and refining. by testing ideas and learning from both successes and failures. So the diversity of approaches in quantum gravity is not a problem to be solved. It is a reflection of an active and evolving field. A field that is still searching for the language that can describe the deepest levels of reality. And as we consider these different perspectives, the question of what came before the Big Bang remains open, not because it cannot be asked, but because it may require a new way of thinking to answer, a way of thinking that goes beyond our current frameworks, beyond our familiar concepts of space and time, and into a deeper understanding of the structures that give rise to the universe itself. In that sense, the uncertainty is not a limitation, it is an invitation to continue exploring, to remain curious, and to recognize that at the edge of knowledge there is always more to discover. As we explore ideas about what might lie before the Big Bang, it becomes helpful to pause and gently return to something more grounded. What can we actually observe? Because no matter how imaginative or mathematically elegant a theory may be, it ultimately needs some connection to evidence. And in cosmology, that evidence comes from light, from radiation, and from subtle signals that have travelled across vast stretches of space and time. But there is an important limit. We can only observe a portion of the universe. This region is known as the observable universe, and it is defined by how far light has been able to travel since the beginning of cosmic expansion. Even though the universe is about 13.8 billion years old, the observable universe extends to a radius of roughly 46 billion light-years. This larger distance arises because space itself has been expanding while light travels, stretching the distances between objects over time. Beyond this horizon, there may be more universe. In fact, most models suggest that there almost certainly is, but light from those regions has not had enough time to reach us, so they remain beyond direct observation. This limitation is not just practical, it is fundamental. It defines the boundary of what we can see, measure, and test. Within that boundary, however, we have gathered an extraordinary amount of information. One of the most important sources of that information is the cosmic microwave background. This faint radiation, first detected in the 1960s, provides a snapshot of the universe when it was about 380,000 years old. At that time, the universe had cooled enough for electrons and protons to combine into neutral atoms, allowing light to travel freely. That light has been stretched by the expansion of space, shifting it into the microwave region of the spectrum. Today, it fills the entire sky, with a temperature of about 2.7 degrees above absolute zero. Space missions such as the Wilkinson Microwave Anisotropy Probe, often called WMAP, and the Planck satellite, operated by the European Space Agency, have mapped this radiation in remarkable detail. These maps reveal tiny variations in temperature on the order of 1 part in 100,000. These variations correspond to slight differences in density in the early universe, which later grew into galaxies and large-scale structures. But they also provide clues about the physics of the very early universe. By studying the statistical properties of these fluctuations, scientists can test models of inflation, measure the geometry of the universe, and estimate key cosmological parameters. In some cases, researchers have even searched for patterns that might hint at events that occurred before or during the earliest moments of expansion. For example, certain models of cyclic cosmology predict the existence of circular patterns or unusual correlations in the cosmic microwave background. These signatures would be extremely subtle, and interpreting them is challenging, but they represent one possible way of looking beyond the standard picture. Another promising avenue comes from gravitational waves. Unlike light, which can be scattered or absorbed, gravitational waves are ripples in space-time itself. They were predicted by Albert Einstein as part of general relativity, and were first directly detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, known as LIGO. These detections came from the mergers of black holes and neutron stars, events that produce powerful disturbances in space-time. But there is also the possibility of a more ancient signal. Gravitational waves generated during the earliest moments of the universe could, in principle, still be present today as a faint background. This is sometimes referred to as the primordial gravitational wave background. If detected, such a signal could provide information about processes that occurred at extremely high energies, possibly even during inflation or earlier. Experiments are ongoing to search for these signals, using both ground-based detectors like LIGO and future space-based observatories. Another approach involves studying the polarization of the cosmic microwave background. Certain patterns in the polarization, known as B-modes, could be influenced by gravitational waves from the early universe. Detecting these patterns is extremely difficult, requiring precise measurements and careful separation of signals from foreground sources such as dust within our own galaxy. But progress continues, with multiple research groups contributing to the effort. Institutions such as the Perimeter Institute for Theoretical Physics in Canada and the Kavli Institute for Cosmological Physics are actively involved in developing models and interpreting data related to these questions. They bring together physicists, astronomers, and mathematicians, combining theoretical work with observational analysis. Despite these advances, there are significant challenges. The signals we are searching for are often incredibly faint. They can be masked by noise, both from instruments and from astrophysical sources, and even when patterns are detected, interpreting them requires careful analysis to distinguish between different possible explanations. There is also a more fundamental limitation. If certain events occurred before the Big Bang, or outside the region that is causally connected to us, their signals may never reach us. In that case, no matter how advanced our instruments become, direct observation may not be possible. This does not mean that we cannot learn anything about those possibilities. Theoretical models can still provide insights, and indirect evidence may offer clues. But it does mean that there are limits to what observation alone can tell us. This is an important point. Science is grounded in evidence, but it also recognizes its boundaries. When we reach those boundaries, we do not stop asking questions, but we do become more careful in how we interpret the answers. So as we consider ideas about what came before the Big Bang, it is helpful to keep one foot firmly in observation, to remember what we can measure, what we can test, and what remains beyond our current reach. The observable universe provides a rich and detailed picture of cosmic history, from the earliest light to the formation of galaxies and the large-scale structure of the cosmos. It tells us a great deal about how the universe has evolved. But when we look toward the very beginning, and especially beyond it, the picture becomes less certain. And in that space between what we know and what we can only imagine, the question remains open, quietly inviting us to explore further while reminding us of the limits of what we can see. There is a gentle but important question that sits beneath everything we have been exploring. Not what came before the Big Bang, but whether that question itself makes sense. At first, it feels almost too simple to challenge. Of course it makes sense, we might think. Every event has a cause. Every moment follows another. Asking what came before seems as natural as asking what happened yesterday. But as we move closer to the foundations of physics, and even further into the structure of thought itself, this assumption begins to shift. Because the meaning of a question depends on the framework in which it is asked. If the framework changes, the question may need to change with it. This idea is not new. Philosophers have been considering the nature of time for centuries, long before modern cosmology began to take shape. St. Augustine, writing in the 4th century, reflected deeply on the nature of time. He famously observed that when no one asks him what time is, he feels he understands it, but when he tries to explain it, the concept becomes elusive. Augustine also addressed a question that feels surprisingly familiar. What was God doing before creating the universe? His answer was subtle. He suggested that time itself was part of the creation, that there was no before in which events could occur. In other words, the question assumes the existence of time prior to its beginning, and that assumption may not hold. Many centuries later, Immanuel Kant approached the question from a different angle. Kant argued that time and space are not properties of the world as it exists independently of us. Instead, they are forms of intuition, structures of the human mind that organize our experience. According to Kant, we do not perceive the world directly as it is in itself. We perceive it through the lens of space and time. These are the frameworks that allow us to make sense of experience. This idea has interesting implications for cosmology. If our understanding of time is shaped by the way we perceive and think, then applying that concept to the universe as a whole may not always be straightforward, especially when we consider conditions that lie far outside our everyday experience. In modern physics, we have seen that time is not absolute. It can stretch, bend, and even lose its meaning under certain conditions. In general relativity, time is part of space-time, influenced by gravity and motion. In quantum gravity, time may not appear in the fundamental equations at all. and in models where spacetime is emergent, time may arise from deeper processes rather than existing independently. All of this suggests that the concept of before may not be universally applicable. It works well within the domain of everyday experience and even within much of classical physics. But when we approach the earliest moments of the universe, or the deepest levels of physical description, the framework changes. And when the framework changes, the meaning of our questions can change as well. This is where the idea of an ill-posed question comes in. In science, a question is considered well-posed if it can be clearly defined and, at least in principle, answered within a given framework. An ill-posed question, on the other hand, may rely on assumptions that do not hold, or it may not correspond to a well-defined concept. For example, asking what lies north of the North Pole is not a meaningful question within the geometry of the Earth. It uses a direction that is defined only within a certain region and attempts to extend it beyond its domain. In a similar way, asking what came before the Big Bang may rely on the assumption that time extends beyond that point. But if time itself begins at the Big Bang, or emerges from deeper processes, then the concept of before may not apply. This does not mean the question is wrong. It means that its meaning depends on the framework we use. In some models, such as cyclic or bounce cosmologies, the question does make sense. There is a prior phase, a contracting universe, or a previous cycle. In those contexts, before refers to an earlier stage in a larger sequence. In other models, such as those involving emergent time or boundary conditions, the question becomes less clear. There may be no earlier moment in the usual sense. Instead, the Big Bang could represent a boundary or a transition, or a feature of how spacetime emerges. In these cases, asking what came before may be like asking what lies outside a projection. The answer exists, but not within the same set of coordinates. Language plays a subtle role in all of this. The words we use, such as before, after, beginning, and cause, are shaped by our experience of time. They carry assumptions about sequence and direction. When we apply these words to the universe as a whole, especially under extreme conditions, they may not always capture what is happening. This is not a failure of language. It is a reminder of its limits. Scientific progress often involves refining not just our theories, but also the way we frame our questions. Sometimes the most important step is not finding an answer, but recognizing that the question needs to be asked differently. So instead of asking what came before the Big Bang, we might ask how the conditions of the early universe arose, or what underlying principles give rise to spacetime, or how the arrow of time emerges from physical processes. These questions may be better suited to the frameworks we are developing. They may align more closely with the concepts that modern physics provides, and they may lead us further toward understanding. There is something quietly reassuring about this shift. It reminds us that not knowing is not the same as being lost. It is part of the process. As our understanding evolves, so do our questions. And sometimes the act of refining a question brings us closer to the truth than any immediate answer could. So the question we began with remains, but it has changed. Not in its words, but in its meaning. What came before the Big Bang? The answer may depend on how we understand time, space, and the structure of reality itself. And in that sense, the question becomes less about a single moment, and more about the framework in which moments can exist at all. And so, after all of this, we find ourselves returning to the same quiet question. What came before the Big Bang? But it no longer feels quite the same as when we first asked it. At the beginning it seemed straightforward, almost inevitable. If the universe began, then something must have come before. That was the intuition. But as we have explored the ideas that modern cosmology offers, the question has softened, unfolded, and taken on new shapes. Because the Big Bang, as we now understand it, is not simply a moment of creation. It is a description of the early evolution of the universe, a phase of extreme heat and density, followed by expansion, cooling, and the gradual formation of structure. And when we look beyond that phase, we find not a single clear answer, but a landscape of possibilities. Some of those possibilities suggest that there was indeed something before. In cyclic cosmology, as explored by Roger Penrose, Paul Steinhardt, and Neil Turok, the universe may pass through repeated phases, with each Big Bang emerging from the end of a previous cosmic cycle. In bounce models, developed within frameworks such as loop quantum gravity, By researchers like Abhay Ashtekar, the universe may have undergone a prior contraction, reaching a minimum scale before expanding again. In these views, the Big Bang is not the beginning, it is a transition, a moment where one phase gives way to another. Other ideas take a different direction. In the context of eternal inflation, developed by Andre Linde, the universe may be part of a vast multiverse, where new regions are continually forming. Each region, each bubble universe, has its own beginning. Our Big Bang may simply mark the start of our local patch, rather than the origin of everything. In string theory and brain cosmology, explored by Edward Witten, Leonard Susskind and others, the Big Bang could be the result of interactions in higher dimensions. Collisions between brains or transitions in a higher dimensional space might give rise to the conditions we observe. Here, what came before is not an earlier time within our universe, but a process unfolding in a larger hidden structure. There are also ideas that move even further away from the notion of a classical beginning. In quantum cosmology, as developed by John Wheeler, Bryce DeWitt, and Alexander Vilenkin, the universe may emerge from a quantum state, where time itself is not defined in the usual way. The concept of before may not apply because the framework in which before has meaning has not yet come into existence. Similarly, in approaches that treat time as emergent, such as those proposed by Julian Barber, Carlo Rovelli, and Fotini Markopoulou, time arises from deeper relationships or structures. In these models, asking what came before the Big Bang may be like asking what came before time itself. And then there are perspectives that shift the focus entirely, ideas that treat the universe as an informational structure, as suggested by John Archibald Wheeler and Seth Lloyd, or as a holographic projection, where the three-dimensional world emerges from information encoded on a boundary, as proposed by Gerard 't Hooft, Leonard Susskind, and Juan Maldacena. In these views, the origin of the universe is not a moment in time, but a condition, a pattern, or a configuration. Something that gives rise to space-time rather than existing within it. And even more intriguingly, there are proposals that connect the birth of universes to black holes. In Lee Smolin's Cosmological Natural Selection, and in models explored by Nikita Poplawski, each black hole could give rise to a new universe. Our own universe might then be the interior of a black hole formed in another, parent universe. In that case, what came before the Big Bang would not be a moment in our past, but a different universe entirely. Each of these ideas offers a different answer, and yet none of them stands alone as a definitive explanation. They coexist, they overlap, they compete, they complement, and they reflect the fact that we are exploring a boundary, a place where our current understanding reaches its limits. There is something important in that. Science is often imagined as a process of steadily replacing uncertainty with certainty. But at its edges, science looks different. It becomes a process of mapping possibilities, of testing ideas, of refining questions, and sometimes of learning that a single answer may not be the right goal. The question of what came before the Big Bang sits exactly at this boundary. It is not fully answered, but it is not empty either. It is rich with insight. It reveals how our understanding of time, space, and reality has evolved. It shows how deeply connected different areas of physics have become, and it highlights the ways in which our most basic intuitions can be challenged and expanded. There is also something quietly beautiful about the coexistence of these ideas. Each one offers a different perspective, a different lens through which to view the universe, and together they form a kind of mosaic, not a single picture, but a collection of possibilities that, when taken together, give a deeper sense of the whole. So as we return to the question, we can hold it a little more gently. What came before the Big Bang? It may have been a previous universe, or a quantum fluctuation, or a higher dimensional interaction, or an informational state. Or it may be that the concept of before does not apply in the way we expect. And perhaps the most honest answer at this moment is that we do not yet know. But in that not knowing, there is no emptiness. There is curiosity. There is exploration. There is the quiet recognition that the universe is deeper and more subtle than any single description can capture. And as we approach the edge of what we can understand, the mystery does not close. It remains open, inviting us to keep looking, to keep questioning, and to keep expanding the way we think about the cosmos. Gently, patiently, and with a sense of wonder that does not need to be resolved to be meaningful.